So let's consider a problem in which we have a mass M connected to a spring constant K, and we have a little small mass, little m, moving some initial V naught, and what happens is the little m hits the big M, and now we have a collision. And so when it collides, it pushes on the mass, squeezes the spring, and so now the spring is going to start oscillating back and forth. So what we want to do is, for this problem, where it hits and then causes it to move, okay, it's going to be oscillating back and forth. I want to know what is the amplitude and what is the frequency of the oscillation, and for that matter, I might even want to know what's the energy of the oscillation. So what we need to know are a couple things to begin with. We need to know what the masses are for these things. We need to know the spring constant, and we need to know the initial mass of the initial velocity of the small object. So let's say the small object has mass 0.25 kilogram. Let's say the big object has mass 1.55 kilograms. Let's say the initial velocity of the small thing is 14.5 meters per second, and let's say the spring constant is 81.6 newtons per meter. Okay, and with that, we are ready to go. Okay, so for the very first part of the problem, then what we have is we have a totally inelastic collision. And so we have mv naught equals m plus big M times v. So v equals mv naught over m plus m, and so that's going to equal 0.25 kilograms times 14.5 meters per second divided by 0.25 kilograms plus 1.55 kilograms, and so that comes out to be equal to 2.01 meters per second. Okay, and so the next question would be, well, in that case, what is going to be the amplitude? When it hits, it is going to be at the equilibrium position. So that means that x equals 0, but there's a velocity of 2.01 meters per second. So that means it's going to be moving to the right, and when it moves to the right, it's going to squeeze the spring and stop when it has reached x equals the amplitude. At that point, the velocity will be 0, and then it's going to start going back and forth, back and forth. And so we can then say that we can compare conservation of energy because the spring forces are conservative. So we can have this as the initial and this as the final situation. So K initial plus U initial equals K final plus U final. So initially the x is 0, so this is going to be 1/2 mv squared, and at the end it's going to be 1/2 kx squared. Well, the x is a, so this is 1/2 mv squared, or I can actually, I guess, put this on the next slide, make more room. So 1/2 mv squared equals 1/2 kx squared, but the x is going to be a. So the 1/2s cancel, and so a is going to be equal to v times square root m over k. And so the a is going to be 2.01 meters per second times the square root of, now the total m, in this case the m is going to be the total mass. So that's going to be, because this is what's moving, so the 0.25 kilograms plus the 1.55 kilogram. So that means that the m is going to be equal to, the m is going to be equal to 1.80 kilograms. So this is 1.80 kilograms, and then we divide by the 81.6 newtons per meter that was given, And so the amplitude of the oscillation is 0.299 meters. Okay. So a couple other questions. What was the period or the frequency of the oscillation? So to find the frequency, that's 1 over the period. So the period was 2 pi times the square root m over k. So that's going to be 2 pi times the square root of the 1.8 kilograms divided by 81.6 newtons per meter. And so the period is going to be equal to 0.933 seconds. Okay, we know that the frequency is 1 over the period, so that would be 1.07 hertz. Okay, final question. What's the energy of the oscillation? Well, the energy of the oscillation is going to be 1/2 Ka squared. So that'll be 1/2 times 81.6 newtons per meter times the 0.299 meters squared. And so that comes out to be 3.65 joules. Okay, and so there is an example of a collision involving a mass on a spring.